An experimental technique related to infrared spectroscopy, but a little different, is called Raman spectroscopy. Raman spectroscopy is not an absorption technique in contrast to the two absorption techniques we talked about so far, the rotational and infrared. Instead, Raman spectroscopy is a light scattering technique. And the idea is you shine light, very monochromatic light, onto a sample. And then the light that comes out of the sample is shifted in frequency, and the frequency that is shifted, it corresponds to differences in vibrational energy levels. Let's just see what we mean by that. So here is light coming in, h nu, at a particular frequency. Here's our sample molecule, and the light coming out we're going to put into through a monochromator. And what we'll find, if we look at the spectrum, this is energy on this axis, is that we get the light at the same frequency coming in. Let's call this h nu 0. So this would be the light that just went right through the sample and didn't interact. But what you'll find is you'll have on this side, you'll have some lines, and then you have the mirror image over here on this side. And these differences in energy here, little delta E, which corresponds to a difference in frequency, is related to the vibrational energy levels. So it's a transition between vibrational energy levels. Now, the one way how one explains that is that here you have system. These are vibrational energy levels. This is energy going up this way. This would be the vibrational energy corresponding to 0, 1, 2 quantum number, and so on. One postulates a virtual state, these chemists, virtual state. So the electric field of the light, remember light has a transverse electric field which oscillates this way, will oscillate these electrons in this molecule. So the electrons will follow the electric field as it oscillates back and forth, and it'll go to a high energy state, and then, let's say, go up from here to this virtual state, and then it goes from the virtual state not back down to 0, but it goes down to a higher vibrational energy level. So the light going in was high energy, the light coming out is lower energy, and that shift in energy corresponds to this difference in energy here. One can also start at this vibrational energy level, go up here, and then one goes from that energy level down here. And therefore, the energy that's coming out of the system is greater than the energy going into the system, and therefore you have these lines up here. These lines are called the Stokes lines, and the lines at higher energy are called the anti-Stokes line. So essentially you get a vibrational spectrum by the shifts in frequency from your incoming light. What is governing this, what allows you to do this? Well, the polarizability of the electron cloud around the molecule. So this is an electron cloud here. And polarizability means how easily the electrons can move in response, or by what amplitude the electrons can move in response to an oscillating electric field. Electrons that are very easily polarized will oscillate a lot compared to electrons that are not easily polarized, where they won't oscillate as much. So that's Raman, basically Raman spectroscopy. Now, I've been teaching this course for quite a long time, and I've noticed that sometimes students get a little confused about Raman, the spectroscopist who invented or discovered Raman spectroscopy, and Raman the noodle. These two things are different, so don't be confused. It's not Raman spectroscopy, it's Raman spectroscopy. Selection rules. Selection rules are exactly the same for Raman as they are for infrared absorption spectroscopy. The change in quantum number has to be plus or minus 1. And also a gross selection rule. Remember, for infrared spectroscopy, the vibrations had to give rise to a oscillating dipole moment. Well, for this, the corresponding gross selection rule is electron polarization has to change during a vibration. So you have ability to move the electrons around the electric field, and the way the electrons move has to change when you have a vibration. Now for infrared absorption spectroscopy, what we had was we looked at the irreducible representation corresponding to a particular vibration, and then we looked in the character table and saw whether one of the Cartesian coordinates was transformed or had the same irreducible representation as that irreducible representation for a normal mode. And if they did, then we said that that particular irreducible representation, that vibration, the normal mode corresponding to that, was IR active. Corresponding to that for Raman spectroscopy is not just X or Y or Z, it's a second order, X squared, Y squared, XY, and so on. If the irreducible representation of the normal mode corresponds to one of these, then you would say that irreducible representation corresponding to the normal mode, that normal mode is Raman active. So instead of XYZ is X squared, Y squared, Z squared, X times Y, X squared minus Y squared, Z squared, and so on. Well, let's just look at, try to get that through here. Which of the normal modes of water are or is Raman active? All right, let's look at water. So remember, water had three normal modes, and we'll just reproduce those here. There was this symmetric stretch. There was the asymmetric stretch, where this stretched this way, but this went this way, and this went this way. And then there was that wagging motion, where, sorry, this is an H. This went in, this H, that went in, and that went up a little bit. And we saw that this was A1, this was B2, and this was A1. All right, so let's see if the one of these two irreducible representations, A1 and B2 for these normal modes, whether that has the same irreducible representation as a second order Cartesian axis in the character table. So here's the character table, C2V. We're looking for A1 and B2, is that correct? Yes, A1 and B2. A1, oh look, in the character table, X squared, Y squared, and Z squared have the same irreducible representation, A1. So therefore, any normal mode in water that has A1 irreducible representation is Raman active, because that's X squared. Let's look at B2. Here's B2. B2 has YZ, so the YZ plane has an irreducible representation like B2, which is this one here. So this one is also active, has the same irreducible representation as a second order Cartesian plane in the character table. All normal modes are IR active. Now let's take another look here. How about CO2? Is the IR inactive mode of CO2 Raman active? So recall, we had carbon dioxide. We had a symmetric stretch of carbon dioxide where this one went out this way, this one went out this way. This did not result in any change of dipole moment, so therefore this is IR inactive. And we saw that this was the sigma, no, that's not a sigma. This was the sigma G plus. And again, this was the D infinity H point group. So let's see if any second order Cartesian system transforms or has the same irreducible representation as sigma G plus. So here's the D infinity H point group character table, and here we have sigma G plus, a totally symmetric. Oh look, X squared plus Y squared and Z squared. So sigma G plus has not only the a symmetric stretch of CO2, but it also has this x squared plus y squared and z squared. So this would be Raman active. So even though you cannot see this stretch in an infrared spectrum, if you did a Raman spectrum, you would see it. All right, so maybe we know something about Raman spectroscopy. And I'd just like to emphasize again that Raman spectroscopy is not an absorption spectroscopy. You're not absorbing light to go directly from one energy state to another. In fact, it's a light scattering technique. Let's take a closer look at why one has to look at second order notations in Cartesian coordinates in order to determine whether something is Raman active or not. Okay, what happens when you have a light coming into a sample? Here's our sample, and we have an electric field this way. Direction of light is that way. This electric field oscillating up and down, is that the electrons are polarized, and the electrons say are initially up this way, something, but then as they interact with the electric field of light, they go up and down, and in general light could be one way or polarized the other way in the x or y direction. If this is a z direction, this is plain polarized light, and in general you could say it's polarized one way or another. So what one has is let's write this way as a dipole, the dipole. So this is transformed or pushed one way to form a dipole in the x direction, the dipole in the y direction, and the dipole in the z direction. So that's what's induced, and you have coming into that electric field in the x direction, electric field in the y direction, electric field in the z direction. Well, note that for plain polarized light, you don't have x or y, you have x and y, but you don't have z. So if we want to couple these two, we can just put 0, 0, 1 here, 0, 0. All right, so the z won't be affected at all. However, let's look at the x. So we have an electric field here, and not necessarily will the electrons be shifted in the x direction because they might be bound to various atoms and so on. So it could be that if you have an oscillation in the x, the electrons, oscillation of the electric field in the x direction, the electrons could be actually moved over into the y direction. So what you'll have are off-diagonal terms which couple the electric field with the way the electrons move when they're polarized. So the fact that these are off-diagonal elements means you need a 2 by 2 matrix. So x couples with x and y couples with x and y. This implies that you need x and y together, or x squared or y squared, or some other second order Cartesian coordinates in order for the electric field to make an electrons move either in the x direction or y direction. So that's why you need these second order terms.